Right now, the farthest human-made object ever launched is drifting through interstellar darkness at over 38,000 miles per hour. It has been traveling for nearly 50 years, and it has not even crossed 1% of the distance to the nearest star. That single fact should stop you cold, because the distances we are about to explore do not simply get larger, they change what distance means. Each new scale destroys a different part of how your brain understands reach, travel, survival, and connection. By the end, you will understand why the universe is not just big. It is built in layers of separation so severe that the farther you look, the more reality itself begins to feel organized around what can never be crossed, reunited, or fully known. If this kind of journey through the deepest scales of reality is something you want more of, a like and subscribe genuinely helps this channel reach new people. It takes a moment and it means a lot. Are you comfortable? Let's begin. Most people believe they understand how far away things are in space. They have seen the diagrams, the neat little circles showing Mercury, Venus, Earth, Mars, all the way out to Neptune, arranged on a page like beads on a string. The gaps look manageable. The solar system looks like a neighborhood. It is not a neighborhood. It is a desert so vast that every object in it, every planet, every moon, every asteroid and speck of frozen dust is separated from everything else by stretches of emptiness that would crush any intuition you brought with you from life on the ground. And the moment you try to treat those distances seriously, using real speeds, real fuel, real human lifetimes, the comfortable picture on the page collapses. What replaces it is something most people have never actually confronted. Not the idea that space is big, but the specific, concrete reality of how far away the nearest things actually are, and what that means for anything you might ever want to do about it. We will start close. Closer than you think matters, because even here, even inside the system we call home, the distances are already enough to break the first layer of how your brain processes reach and scale. And what breaks here is only the beginning. Start with the distance from Earth to the Moon. It is roughly 240,000 miles. That number sounds modest by space standards, and in a sense it is. Light covers it in about 1.3 seconds. The Apollo missions crossed it in roughly 3 days. It is the only destination beyond Earth that human beings have ever physically visited. By any honest standard, the Moon is the single place in the universe where human travel has actually worked. Now, move outward. The distance from Earth to the Sun is approximately 93 million miles. Light covers that gap in about 8 minutes. That means when you look at the Sun, you are not seeing it as it is right now. You are seeing it as it was 8 minutes ago. If it vanished this instant, you would not know for 8 minutes. You would still feel warmth on your skin from a star that no longer existed. 8 minutes of sunlight with nowhere to go. That 93 million mile distance is called 1 astronomical unit. It is the basic ruler astronomers use for measuring everything else inside the solar system. And already, even at this first step, the numbers start to pull away from anything a human life can relate to. If you could drive a car at highway speed, 70 miles per hour, non-stop, no fuel, no rest, no aging, it would take you roughly 152 years to reach the Sun. A person born on that highway would die on that highway, and their grandchildren would die on that highway, and nobody in the car would ever arrive. That is the distance to the nearest star. Our star. The one that is right here. Before we leave for the outer solar system, Consider Mars. Mars is the destination humanity talks about most. It is the planet with the rovers, the one with the plans for crewed missions. Most people think of Mars as close. It is not. At its nearest approach, when Earth and Mars align on the same side of the Sun, the distance between them is roughly 34 million miles. At its most distant, when the two planets sit on opposite sides of their orbits, that gap stretches to roughly 250 million miles. Even at its closest, light takes over 3 minutes to cross the distance. A radio signal from a rover on the Martian surface takes between 3 and 22 minutes to reach Earth, depending on orbital positions. That means every command sent to a Mars rover is already old by the time it arrives. Every image received on Earth shows Mars as it was minutes ago. You cannot drive a Mars rover in real time. You send instructions, you wait, you hope the rover did not encounter something unexpected during the minutes it took your command to arrive. A crewed mission to Mars, using current or near-future propulsion technology, would take roughly 7 to 9 months each way. The astronauts would spend over half a year coasting through the vacuum between two planets, farther from Earth with every passing hour, watching their home shrink to a bright blue dot and eventually to a point of light indistinguishable from the stars around it. During large portions of the transit, real-time conversation with mission control would be impossible. The crew would ask a question and wait 10 minutes, then 15, then 20 for the answer to arrive. By the time they reach Mars, the delay would be long enough that in any emergency, they would need to solve the problem themselves or die waiting for instructions. And Mars is close. Mars is the easiest destination beyond the Moon. Mars is the low-hanging fruit of interplanetary exploration, the next small step in a solar system that extends thousands of times farther than the Mars orbit in every direction. If this is what close looks like, if even the nearest and most accessible planet beyond Earth already introduces delays and distances that strain human mission design to its limits, then what comes next should make you uneasy. Now go further. Go to Pluto. When NASA's New Horizons spacecraft launched on January 19th, 2006, it tore away from Earth at approximately 36,000 miles per hour. That made it the fastest object ever launched from this planet at the time. It was moving so quickly that it passed the Moon's orbit in just 9 hours. Most spacecraft take days to reach the Moon. New Horizons did it before the launch day news cycle was over. At that speed, with a gravity assist from Jupiter that pushed it even faster, New Horizons still took 9.5 years to reach Pluto. 9.5 years, the fastest thing we had ever thrown into space, racing at a velocity that would carry you from New York to Los Angeles in roughly 4 minutes, needed nearly a decade to reach a world that most diagrams show as just a few inches from Neptune. Here is where the first crack appears. When New Horizons arrived at Pluto on July 14th, 2015, the dwarf planet was approximately 3.1 billion miles from Earth. A radio signal traveling at the speed of light took 4 hours and 25 minutes to carry the confirmation of closest approach back to mission control. The team at the Johns Hopkins Applied Physics Laboratory had to wait that long just to learn whether the flyby had succeeded. 4.5 hours of silence, hoping that a spacecraft they could not see or control in real time had correctly executed a sequence they had uploaded days before. That delay at Pluto was uncomfortable, What is happening right now with the Voyager One is something closer to a slow-motion farewell. Every instruction sent to Voyager One travels through NASA's Deep Space Network, a collection of massive radio antennas positioned at 3 sites around the globe in California, Spain, and Australia. Spaced so that at least one station always has a line of sight to the spacecraft as the Earth rotates. The signal leaves the antenna at the speed of light. Then the engineers wait. As of today, they wait over 23 hours for that signal to arrive. If they need a response, they wait another 23 hours for Voyager 1's faint reply to travel back. A single round-trip exchange, 1 question and 1 answer, takes nearly 2 full days. The spacecraft's transmitter operates at roughly 23 watts. That is less power than a refrigerator light bulb. By the time that signal reaches Earth, it is spread across such an enormous volume of space that the power arriving at the antenna is so faint that collecting it continuously for millions of years would not generate enough energy to light a single flashlight for 1 second. The Deep Space Network's receivers are among the most sensitive listening devices ever built. They have to be. They are trying to hear a whisper from 16 billion miles away, and the conversation is ending. The plutonium that powers Voyager 1 decays at a fixed rate. Each year, the generator produces roughly 4 fewer watts of electricity. NASA has already turned off heaters, shut down cameras, and deactivated instruments one by one to keep the most critical systems alive. The spacecraft that once photographed Jupiter's Great Red Spot and the rings of Saturn in breathtaking detail is now flying blind. Its cameras dark, its remaining instruments counting particles and measuring magnetic fields with the last trickle of power available. By the early 2030s, there will not be enough electricity to power even a single instrument. The transmitter will go silent. The Deep Space Network antennas will listen and hear nothing. And Voyager 1 will continue on, a dead ship moving at 38,000 miles per hour, carrying a golden record etched with sounds and images of Earth. A message meant for anyone who might find it. No one ever will. The distances involved make the odds of interception effectively 0. The record will outlast the Earth itself, drifting through interstellar space for billions of years, but it will never be played again. That is what distance does at the scale of the outer solar system. It does not just make things hard. It makes things final. The spacecraft we sent to explore the planets is becoming a monument to the limits of how far our reach actually extends. And its current position, roughly 163 astronomical units from the Sun, is not even a rounding error compared to the true size of the space it is trying to cross. That experience, that gap between action and knowledge, is what distance actually feels like when it becomes real. And Pluto is not far. Pluto, by the standards of what we are about to cover, is embarrassingly close. It orbits within the inner suburbs of the solar system. Everything beyond it stretches into territory that makes the Pluto distance feel like a walk to the mailbox. Beyond Neptune and Pluto lies the Kuiper Belt, a wide band of icy objects left over from the formation of the solar system, extending from roughly 30 astronomical units to about 50 astronomical units from the Sun. New Horizons flew through part of it, visiting a small frozen world called Arakoth on January 1st, 2019, at a distance of approximately 4.1 billion miles from Earth. Arakoth looked like a reddish snowman, 2 lumps of primordial ice fused together in the cold, untouched since the planets were born. It was the most distant object a spacecraft had ever visited up close. But the Kuiper Belt, as vast as it is not the edge. It is not even close to the edge. Beyond the Kuiper Belt, beyond all the known planets and dwarf planets and scattered icy bodies, the solar system keeps going. It keeps going for a distance so extreme that the entire planetary region, everything from Mercury to Pluto and beyond, fits inside it the way a grain of sand fits inside a cathedral. This is the Oort cloud. The Oort cloud is a theoretical shell of trillions of icy objects that surrounds the Sun in a vast sphere. No one has ever seen it directly. No telescope has ever imaged a single object within it. Its existence is inferred from the behavior of long-period comets. Comets that plunge toward the Sun from enormous distances on orbits that take thousands or even millions of years to complete. The Dutch astronomer Jan Oort proposed its existence in 1950, and every subsequent observation of cometary trajectories has supported the idea. The inner edge of the Oort cloud is estimated to begin at roughly 2,000 astronomical units from the Sun. The outer edge may extend to 100,000 astronomical units or more. Some estimates push it as far as 200,000 astronomical units. To give that a number in more human terms, the outer boundary of the Oort cloud may sit roughly 3 light years from the Sun. 3 light years. That is approximately 18 trillion miles. This means the solar system, the thing we call home, is not a compact disk of planets huddled around a warm star. It is an enormous sphere of gravitational influence, stretching light years into the darkness. The planets are a tiny bright cluster at the very center. Everything beyond them, for trillions upon trillions of miles in every direction, belongs to the Oort cloud. It is the Sun's territory, held together by gravity so faint at those distances that a passing star can steal comets from the outer edges, simply by drifting nearby. If you place the Sun at one end of a football field and shrank the entire solar system to fit, the planets, all of them, from Mercury to Neptune, would be clustered within the first inch of the goal line. The Oort cloud would stretch all the way to the far end zone and possibly into the parking lot. That is the scale mismatch between the part of the solar system we know and the part we have never seen. And here is where it starts to become personally unsettling. We have a spacecraft out there right now, older than most of the people who will ever hear this, still transmitting, still sending data, and it has covered almost none of this distance. Voyager One launched on September 5th, 1977. It visited Jupiter in 1979 and Saturn in 1980. After its Saturn flyby, it was flung upward out of the plane of the planets on a trajectory that will never bring it back. It has been traveling away from Earth ever since. For nearly 50 years, moving at roughly 38,000 miles per hour, it has been heading outward into the dark. As of right now, Voyager One is approximately 15.8 billion miles from Earth. A radio signal sent from NASA's Deep Space Network takes over 23 hours to reach it. In November of 2026, the spacecraft is projected to cross a milestone that sounds almost poetic. It will be 1 light day away from Earth. That means a message sent to Voyager 1 in the morning will not arrive until the next morning. A full day for light itself to make the trip. A full day at the fastest speed the universe allows. That milestone is remarkable. It is also, in the context of the Oort cloud, humbling to the point of cruelty. Voyager 1 is currently at roughly 170 astronomical units from the Sun. The inner edge of the Oort cloud begins at approximately 2,000 astronomical units. At its current speed, Voyager One will not reach the inner edge of the Oort cloud for roughly another 500 years, and crossing the Oort cloud itself, passing through it from the inner boundary to the outer boundary, would take approximately 30,000 years. 30,000 years. That is longer than all of recorded human civilization. Longer than the entire span from the invention of agriculture to this moment. And at the end of those 30,000 years, Voyager 1 would finally exit the sun's gravitational domain and enter true interstellar space. Not the technical interstellar space it crossed in 2012, when it passed through the heliopause and left the bubble of solar wind. The real interstellar space, the space between the sun's sphere of influence and the sphere of influence of the next star. It would still not be anywhere near that next star. This is what the solar system actually looks like when you take it seriously. Not a diagram. Not a poster on a classroom wall. A territory so vast that the fastest object humanity has ever sent into the void will spend longer crossing our own backyard than human beings have spent building cities. And the spacecraft itself is dying. Voyager 1 is powered by a radioisotope thermoelectric generator, a device that converts heat from the decay of plutonium-238 into electricity. That plutonium is running out. The power output drops by roughly 4 watts per year. NASA has already shut down most of Voyager 1's instruments to conserve energy. By the early 2030s, possibly sooner, there will not be enough power left to run any instruments at all. The transmitter will fall silent. The spacecraft will continue moving. A dark piece of metal drifting at 38,000 miles per hour through the emptiness. But it will no longer be talking to us. When that happens, the farthest human-made object will become a ghost. It will still be out there. It will still be crossing the distance toward the Oort cloud. But no one will know exactly where it is. No one will hear from it again. It will spend the next 10,000 years, the next 100,000 years, the next million years, coasting through the darkness on a trajectory that will carry it generally in the direction of a star in the constellation Camelopardalis. It will arrive in the vicinity of that star in roughly 40,000 years. It will not stop. It will drift past and continue into the galaxy alone. This is what the solar system does to human ambition. We built the fastest thing we could. We gave it nearly 5 decades of running time. And it has not even left the front yard. That is not a metaphor. It is a measurement. But there is something even more disorienting about these distances than the raw numbers. It is what the distances do to the concept of here. When you stand on Earth and look up at the night sky, your brain tells you that you are somewhere. You are at a location. The stars are out there, at other locations, and between you and them, there is distance. Simple, crossable distance. The kind you experience every day when you walk across a room or drive across a city. That intuition is wrong. Not slightly wrong. Fundamentally wrong. Inside the solar system, distance is already large enough that it breaks the link between seeing something and being able to reach it. You can see Pluto through a good telescope, you can photograph it, you can know its composition, its temperature, its orbital period. But reaching it took the fastest spacecraft ever launched nearly a decade, and no human being has ever gone there or is likely to go there within the lifetime of anyone alive today. The Oort cloud is worse. You cannot see it at all. You can only infer it. It is a place defined entirely by gravitational mathematics and the orbits of comets that occasionally fall inward. It surrounds you in every direction, but it is invisible, unreachable, and so far away that the only object we have ever sent in its general direction will not arrive for 3 centuries. And the Oort cloud is still inside the solar system. It is still home. It is still bound to the sun by gravity. Everything we have discussed so far, every distance that has already outrun human intuition and human engineering and human lifespan, is contained within the gravitational neighborhood of a single ordinary star in the outer arm of a single ordinary galaxy. This is the first distance that breaks your brain, not because the number is large, you have heard large numbers before, but because the number is attached to something real. A spacecraft, a mission, a clock ticking down to silence, and the distance is attached to a boundary that matters, the boundary between our star's reach and everything beyond it. A boundary so far away that nothing we have ever built has come close to crossing it. But here is the part that turns the stomach. Everything we have just covered, all of it, from the Earth to the Moon, from the Moon to the Sun, from the Sun to Pluto, from Pluto to the Oort cloud, every mile, every year, every dead spacecraft drifting in the dark, is nothing compared to what comes next. The nearest star beyond our Sun is Proxima Centauri. It sits 4.24 light years away. That is approximately 25 trillion miles. If you took the entire distance from the Sun to the outer edge of the Oort cloud and used it as a measuring stick, you would need to lay it down end to end, roughly 1 1/3 times, just to reach Proxima Centauri. At Voyager One speed, the crossing would take over 73,000 years. That number does not describe a journey. It describes an impossibility. And on the other side of that impossibility, there is not a destination waiting. There is another star, surrounded by its own Oort cloud, its own territory of trillions of icy objects, its own vast sphere of gravitational emptiness. And beyond that star, another gap. And beyond that gap, another star. And between every pair of stars, the same crushing, impassable nothing. Everything we thought we understood about distance. Everything we calibrated by driving to work, or flying across the ocean, or watching a spacecraft reach Pluto, was a training exercise for a reality that does not scale. The solar system taught us that distance is large. What lies beyond the solar system will teach us that distance is something else entirely. Something that does not just increase, something that changes category, something that stops being a number and starts becoming a wall. And the wall begins right here, at the edge of our own sun's reach, where the last comets lose their grip and the light from home fades to a point indistinguishable from every other star in the sky. What waits on the other side of that wall is the subject of what comes next. And it is worse than you think. We left Voyager One drifting at 38,000 miles per hour toward the edge of the solar system, centuries away from even reaching the inner boundary of the Oort cloud. And we introduced a single number that changed the stakes entirely. 4.24 light years, the distance to Proxima Centauri, the nearest star beyond our sun. Now it is time to cross that distance, or rather, to try. Because what happens when you actually attempt to calculate a journey to the closest star in the entire galaxy is not frustration. It is a category shift. The problem does not get harder in the way that climbing a taller mountain is harder than climbing a shorter one. It changes into a different kind of problem altogether. The rules that governed everything inside the solar system, mission planning, fuel budgets, communication delays, stop being the main obstacle. The main obstacle becomes time, not mission time, not career time, civilizational time, and once you understand what that means, you will never look at the night sky the same way again. Let us begin with what Proxima Centauri actually is. Proxima Centauri is a red dwarf star in the constellation Centaurus. It is the closest known star to our Sun, sitting at a distance measured by the European Space Agency's Gaia mission at 4.2465 light-years, with uncertainties so small they barely matter for any practical purpose. In raw numbers, that translates to approximately 25 trillion miles. 25 followed by 12 zeros. A number so large it resists every effort to make it feel real. Proxima Centauri is part of the Alpha Centauri star system, a triple star arrangement that includes Alpha Centauri A, a star similar to our Sun, and Alpha Centauri B, a slightly smaller and cooler companion. Those two stars orbit each other relatively closely. Proxima Centauri orbits the pair from a much greater distance, loosely bound by gravity, taking hundreds of thousands of years to complete a single orbit. It is the runt of the trio, only about 1/8 the mass of our Sun, roughly 50% larger than Jupiter in diameter, and so dim that despite being the closest star to our solar system, it is completely invisible to the naked eye under any sky conditions. You would need a reasonably capable telescope just to see it. And yet this faint, cold, flickering red dwarf has become one of the most studied stars in modern astronomy. Because it has planets. In 2016, the European Southern Observatory announced the discovery of Proxima b, a roughly Earth-mass planet orbiting Proxima Centauri within its habitable zone, the region where temperatures might allow liquid water to exist on the surface. The discovery electrified the public and the scientific community alike. The nearest star to our Sun had a world that could, in principle, support conditions we associate with life. It was the closest potentially habitable exoplanet anyone had ever found. In 2022, astronomers using the same observatory's Very Large Telescope identified signs of a third planet, Proxima d, a tiny world only about a quarter the mass of Earth, orbiting extremely close to its star and completing one orbit every 5 days. In 2025, Proxima d was formally confirmed using the Near-Infrared Planet Searcher instrument. 2 confirmed planets and 1 disputed candidate. One of the confirmed worlds sits in the habitable zone, orbiting a star that is, by cosmic standards, right next door. And we cannot get there. That sentence is not a technological complaint. It is not a statement about budget priorities or political will or engineering limitations that might be solved in a century or two. It is a confrontation with a kind of distance that does not bend to ambition. Let us do the math plainly. Voyager One, the fastest object we have ever sent on an outbound trajectory from the solar system, travels at approximately 38,000 miles per hour. At that speed, the journey to Proxima Centauri would take roughly 73,000 years. If Voyager 1 had launched in the direction of Proxima Centauri instead of toward interstellar space above the plane of the planets, and if it had launched at the peak of the last ice age, roughly 26,000 years ago, it would still not be there yet. Not even close. In the time since that launch, human beings would have invented agriculture, built and destroyed civilizations, developed writing, fought world wars, split the atom, landed on the moon, and launched the James Webb Space Telescope. And Voyager 1 would still be in transit, barely a third of the way there. New Horizons set the record for the fastest launch speed ever achieved leaving Earth, roughly 36,000 miles per hour. even at that blistering departure velocity, far faster than any previous spacecraft had left our planet. The crossing to Proxima Centauri would take over 78,000 years. The spacecraft that reached Pluto faster than anything we had ever built would need longer than the entire history of anatomically modern humans just to reach the nearest star. Doubling the speed cuts the travel time in half, but half of 73,000 years is still 36,500 years. You would need to increase spacecraft speed by a factor of roughly 1,000, reaching a significant fraction of the speed of light before the trip becomes even theoretically achievable within a human lifetime. No propulsion system that has ever been built or tested comes within an order of magnitude of that requirement. There are proposals. Breakthrough Starshot, announced in 2016, envisions using an array of powerful ground-based lasers to accelerate tiny, gram-scale probes attached to light sails to approximately 20% of the speed of light. At that speed, the journey to Proxima Centauri would take roughly 21 years. Add 4.2 years for the signal to travel back. A probe launched today, if the technology worked perfectly, might send back data in about 25 years. But the probes would be the size of postage stamps. They would carry no ability to slow down. They would fly through the Proxima Centauri system at 20% of the speed of light, taking photographs during a flyby that would last a fraction of a second, and then continue onward into interstellar space forever. No orbit, no landing, no sample collection. A brief flash of data from the nearest star, and then silence. That is the best case scenario with speculative technology that does not yet exist. And it only works for a flyby. An actual mission that could enter orbit, study the planets, and send sustained data would require the ability to decelerate from a significant fraction of light speed. A problem that multiplies the energy requirements by orders of magnitude. The physics is not kind. Every kilogram you want to slow down at the destination demands fuel that itself had to be accelerated to the same speed, which demands more fuel to carry that fuel, which demands more fuel still. The numbers spiral upward until the required mass of fuel exceeds the mass of everything available. This is the wall. Not a wall of politics or funding or engineering difficulty. A wall built into the structure of space itself. The distance between stars is so enormous, and the energy required to cross it at meaningful speed is so extreme that even a civilization far more advanced than ours would face constraints that look less like engineering challenges and more like laws of nature. And Proxima Centauri is the closest star there is. Let that settle for a moment. Every other star in the galaxy is farther than this. Most are incomparably farther. The distance we just struggled to conceptualize, the one that defeated every spacecraft ever built, the one that would outlast civilizations, that distance is the minimum. The shortest possible gap between our sun and any other star in existence. Now look at the neighborhood. Within 10 light years of the sun, there are roughly a dozen individual stars scattered across only 7 or 8 star systems. That sounds like a reasonable number until you realize what 10 light years actually means. It means that the volume of space containing those 12 systems is a sphere roughly 20 light years across, encompassing a volume of approximately 4,200 cubic light years. A dozen stars in 7 or 8 systems scattered across 4,200 cubic light years of emptiness. The average spacing between nearby stars in this region is roughly 3 to 5 light years. Those gaps are not filled with anything. They are vacuum. not the partial vacuum of a laboratory or the thin atmosphere at the top of a mountain. The interstellar medium, the gas and dust that drifts between stars, has a density of roughly 1 atom per cubic centimeter. For comparison, the air you are breathing right now contains approximately 25 quintillion molecules per cubic centimeter. The space between stars is not just empty. It is a void so perfect that it makes the best vacuum chambers ever built on Earth look crowded. Try to picture what crossing that void would actually involve. A spacecraft leaving our solar system and heading toward Proxima Centauri would, within a few centuries, pass beyond the Oort cloud and enter a region of space where the sun is no longer the dominant gravitational influence. From that point onward, the ship would be truly adrift. There would be no landmarks, no waypoints, no gravitational signpost to confirm progress. The stars ahead would barely shift position across decades because interstellar distances are so vast that even traveling at tens of thousands of miles per hour produces no perceptible change in the arrangement of the sky. The ship would be surrounded by the interstellar medium, a thin haze of hydrogen atoms, helium, trace molecules, and microscopic dust grains. In practical terms, the spacecraft will be moving through nothing. Not near nothing. Not almost nothing. A void so complete that if you could somehow stand outside the ship and hold out your hand, you might wait years before a single atom struck your palm. There would be no sound, obviously, but there would also be no reference frame for motion. No wind, no friction, no sense of speed. The stars would hang motionless in every direction, unchanging decade after decade. The sun would shrink behind you, dimming from a bright star to a faint one, to a point indistinguishable from the background. And the star ahead, Proxima Centauri, would grow no brighter for centuries, because the distance remaining would still be so enormous that the progress would be invisible. A crew aboard such a ship, if there were a crew, would spend their entire lives watching a sky that appeared completely frozen. And the environment would not be benign. The interstellar medium is threaded with cosmic rays, high-energy particles accelerated by supernova explosions and other violent events across the galaxy. These particles travel at nearly the speed of light and carry enough energy to damage electronics and living tissue. Inside the solar system, the sun's magnetic field and solar wind create a protective bubble called the heliosphere that deflects most of these particles. Beyond the heliosphere, that protection vanishes. A spacecraft in interstellar space would be exposed to the full cosmic ray flux. A constant bombardment of radiation with no shielding except whatever the ship carried with it. The temperature of the interstellar medium varies enormously depending on the environment. Dense molecular clouds, the coldest pockets, sit at roughly 10 to 20 degrees above absolute zero. The diffuse gas between them can reach thousands of degrees, and regions heated by ancient supernova explosions can blaze at millions of degrees. But none of that heat would matter to a spacecraft. The gas is so thin that even at millions of degrees, there are too few particles per cubic meter to transfer any meaningful warmth. This is what lies between every pair of stars in the galaxy. Not a corridor, not a passage. An abyss so featureless, so hostile, and so vast that even describing it in concrete terms risks making it sound more manageable than it is. The interstellar medium is not a place you travel through. It is a place that travel disappears into. And this is the immediate neighborhood. The closest, most tightly packed region around our sun. As you move outward from this tiny cluster, the stars spread further apart. They are not evenly distributed. They clump along the spiral arms of the galaxy and thin out between them. But the fundamental truth remains at every scale. The space between stars is overwhelmingly, crushingly larger than the stars themselves. Now zoom out, all the way out. Look at the galaxy. The Milky Way is a barred spiral galaxy approximately 87,000 light-years in diameter, though some measurements, including the outer halo, suggest it may extend even further. It contains somewhere between 100 billion and 400 billion stars. Our Sun sits roughly 27,000 light-years from the center, on the inner edge of a minor spiral feature called the Orion Arm. Those numbers are among the most quoted in all of popular science, and they are also among the most poorly understood, because the human brain does not process the difference between 1 billion and 100 billion in any visceral way. Both feel like a lot, and the diameter 87,000 light-years sounds like just another big number after you have already heard about trillions of miles. So let us make it concrete. If you could somehow travel at the speed of light, the absolute fastest that anything in the universe can move, crossing the Milky Way from one side to the other would take 87,000 years. A beam of light that left one edge of the galaxy at the moment the first stone tools were chipped in East Africa, roughly 2.5 million years ago, would have crossed the galaxy about 29 times over. But even a beam launched when the Egyptian pyramids were being built, roughly 4,500 years ago, would have barely crossed 1/20th of the disk. The galaxy is so wide that even light, the universal speed limit, cannot cross it within any time span that has meaning in human history. And the Milky Way is not a uniform disk of evenly distributed stars. It has structure, arms, gaps, dense regions, sparse regions, rivers of stars winding through enormous corridors of relative emptiness. Understanding that structure is essential to understanding what the galaxy actually feels like at scale. The Milky Way is a barred spiral. At its center sits a thick, elongated bar of old stars, roughly 15,000 light-years long. From the ends of that bar, major spiral arms wind outward like streams of water spinning off a rotating sprinkler. The arms are not solid structures. They are density waves, regions where stars, gas, and dust pile up temporarily, like traffic bunching on a highway, even though individual cars keep moving. Stars drift into the arms, slow down in the denser environment, and eventually drift out the other side. The arms persist as patterns even though their membership constantly changes. The major arms of the Milky Way include the Perseus arm, one of the two dominant spirals, and the Scutum Centaurus arm on the opposite side. Between and among the major arms lie smaller spurs and branches, including the Orion arm, the modest structure on whose inner edge our Sun currently resides. The Orion arm is not a major feature of the galaxy. It is a minor spur, roughly 10,000 light-years long and roughly 3,500 light-years wide. In the grand architecture of the Milky Way, we live on a side street. The gaps between the arms are not empty in the way that intergalactic space is empty. They contain stars, gas, and dust, but the density drops significantly. Moving from the interior of a spiral arm to the interarm region is like moving from a moderately populated suburb into open countryside. The stars thin out. The gas clouds become scarcer. The bright nebulae and star-forming regions that cluster along the arms give way to quieter, darker stretches where the distance between neighboring stars increases and the sky grows emptier. Near the galactic center, the situation reverses dramatically. Within the central few thousand light years, stellar density increases by orders of magnitude. Stars are packed so tightly that the night sky from a planet in that region would blaze with thousands of stars brighter than Sirius appears from Earth. The core is a crowded, brilliant, violent place, rich with old stars, threaded with magnetic fields, and anchored by the supermassive black hole at its heart. But we do not live there. We live out on the Orion Arm, roughly 27,000 light-years from the center, in a quiet stretch of the disk, where the nearest neighboring star is over 4 light-years away, and the spiral arm we inhabit is a minor feature of a galaxy most of whose interior we will never visit. The Sun completes one full orbit of the galactic center every 212 million years. It has completed roughly 20 orbits since it formed. Each orbit carries it through arm and interarm regions, through denser neighborhoods and sparser ones, on a path that takes longer to complete than the entire age of complex life on Earth. The galaxy is not a static picture. It is a churning, rotating structure whose individual parts move on timescales that dwarf geological epochs, and we sit within it like a single mote of dust, caught in a slow, enormous wheel, circling a center we cannot even see with our own eyes. At the speed of Voyager One, the crossing would take approximately 1.5 billion years. The Sun would complete several full orbits of the galactic center during the trip. Species would evolve and go extinct. Continents would drift into new configurations. The Earth itself might no longer be habitable by the time the journey was done. And yet the Milky Way is not an unusually large galaxy. It is a fairly typical spiral. There are galaxies far larger, far more massive, far more spread out. The Milky Way is home. And home, at the galactic scale, is a disk of stars so wide that light itself takes the better part of 100,000 years to cross it. Inside that disk, the emptiness is staggering. The average distance between stars in the Milky Way is roughly 4 to 5 light years. That average is somewhat misleading because stars cluster more densely in the core and along the spiral arms, and spread more thinly in the gaps between arms. But even in the densest regions of the galaxy, the distances between individual stars are measured in light years. In the sparse regions between the arms, the gaps can stretch to 10 or 20 light years. The galaxy is not a dense cloud of stars pressed together. It is a scattering of hot, bright points, separated by trillions of miles of nothing. If you shrank each star in the Milky Way down to the size of a marble and placed them at the correct relative distances, the nearest marble to our Sun would sit roughly 270 miles away. The galaxy would be a collection of marbles spread across millions of miles of open air, each one separated from its nearest neighbor by hundreds of miles. You could drive for hours without encountering a single one. That is what 100 billion stars actually looks like when you respect the distances between them. Not a crowded city, not a dense field, a scattering so sparse that any individual star, including ours, is overwhelmingly surrounded by nothing. Now consider what sits at the center of all this emptiness. Approximately 27,000 light years from where you're sitting, in a direction we will return to shortly, lies the gravitational center of everything around us. What infrared and radio telescopes have revealed there is extraordinary. At the very core of the Milky Way sits Sagittarius A star, a supermassive black hole with a mass of approximately 4.3 million times the mass of our Sun. In 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A star, a glowing ring of superheated gas swirling around a dark central shadow. The image confirmed decades of indirect evidence gathered by tracking the orbits of stars racing in tight loops around an invisible concentration of mass at the galaxy's core. Sagittarius A star is massive beyond ordinary comprehension, yet physically compact. Its event horizon, the boundary beyond which nothing escapes, spans roughly 16 million miles. That sounds enormous by human standards, but it is tiny compared to the galaxy it anchors. The entire black hole would fit comfortably inside the orbit of Mercury. A monstrous gravitational engine small enough to hide inside the inner solar system, holding 100 billion stars in its gravitational embrace across a disk 87,000 light-years wide. The environment around Sagittarius A star is unlike anything else in the galaxy. Within the central few light-years, stars are packed thousands of times more densely than in our quiet neighborhood on the Orion Arm. Some of these stars orbit the black hole at extraordinary velocities. The star known as S2 completes a full orbit of Sagittarius A star every 16 years, reaching speeds of roughly 2.5% of the speed of light at closest approach. That is over 17 million miles per hour. A single star, many times the mass of our Sun, circling a dark object at a speed that would carry it from Earth to Mars in a matter of minutes. The region is violent. Clouds of superheated gas spiral inward toward the event horizon. Magnetic field lines twist and snap. X-ray flares erupt without warning as matter is shredded by tidal forces and heated to hundreds of millions of degrees. In 2022, the Event Horizon Telescope captured an image of the glowing ring of gas surrounding Sagittarius A star, revealing the shadow of the event horizon itself. The image showed a turbulent, chaotic structure, nothing like the smooth, artistic renderings that populate textbooks. The black hole at the center of our galaxy is not a quiet anchor. It is a maelstrom. And we cannot see any of it with our eyes. The galactic center lies behind the thick disk of the Milky Way itself, obscured by dense clouds of gas and dust that block visible light completely. Astronomers call this region the zone of avoidance, because optical telescopes are blind to it. Everything we know about Sagittarius A star and the dense stellar core surrounding it has been learned through infrared and radio observations that can penetrate the dust. The center of our own galaxy, the gravitational heart of the structure that contains every star and planet we have ever known, is invisible to us in the most basic sense. We live inside a galaxy whose core we cannot see with the light our eyes were built to detect. This adds a layer to the distance that goes beyond simple measurement. The galactic center is not just 27,000 light-years away, it is hidden, obscured by the very structure it anchors. You could point a perfect optical telescope directly at it and see nothing but dark clouds. The distance is compounded by opacity, by the galaxy's own body blocking the view of its own heart. And between us and Sagittarius A star, there is nothing but 27,000 light-years of stars and gas and empty space. At the speed of light, a message sent from Earth toward the galactic center would arrive in 27,000 years. Voyager One, aimed at the center and traveling at its current speed, would take roughly 470 million years. The Sun itself would complete 2 full orbits of the galaxy in that time. This is the second distance that breaks your brain. Not because it is bigger than the first. Of course it is bigger. It is millions of times bigger. But that is not why it matters. It matters because of what it does to the concept of travel. Inside the solar system, distance was a problem of time and fuel. You could, in principle, imagine a faster spacecraft, a better engine, a longer mission. The physics was hard, but the conceptual framework was familiar. You are here, you want to be there, you go. At the interstellar scale, that framework collapses. The distance to Proxima Centauri is not a hard version of the Pluto problem. It is a different kind of problem. The gap between stars is so vast that crossing it requires not just faster ships, but a fundamentally different relationship with time. Any journey measured in tens of thousands of years is not a mission. It is a prayer. A bet that whatever you send will still be functional, still be relevant, still have someone waiting on the other end after an interval of time longer than the recorded history of the species that launched it. And the galaxy is not one gap. It is 100 billion gaps. Every star separated from every other star by light years of vacuum. The Milky Way is not a connected place. It is a vast archipelago where each island is separated from the next by an ocean so wide that crossing it would take longer than the island's civilization has existed. Think about what this means for the question that haunts astronomy more than any other. Are we alone? If there are other civilizations in this galaxy, other beings who look up at their sky and wonder, they are separated from us by the same impossible distances. A civilization orbiting Barnard's star, 6 light years away, might have built telescopes and radio transmitters and launched their own spacecraft, and we would not know. A signal from them, traveling at the speed of light, would take 6 years to arrive. A reply would take 6 years to return. A single exchange of greetings would span more than a decade. And even Proxima Centauri, the nearest destination, may not be welcoming. Despite being small and dim by stellar standards, Proxima erupts with massive flares far more frequently than our Sun. Despite being small and dim by stellar standards, Proxima erupts with massive flares far more frequently than our Sun. In 2021, astronomers detected a flare from Proxima Centauri that was 100 times more powerful than any flare ever observed from the Sun. These events blast the surrounding space with ultraviolet radiation and charged particles, bathing any nearby planet in doses of energy that would strip unprotected atmospheres and sterilize exposed surfaces. Proxima b, the planet that sits in the habitable zone, orbits so close to its star that it completes one full orbit every 11 days. At that distance, it is almost certainly tidally locked, meaning one hemisphere permanently faces the star while the other faces the void. The day side would be baked in perpetual reddish light, punctuated by lethal flares. The night side would be frozen in permanent darkness. Whether any atmosphere could survive the relentless bombardment of stellar radiation remains an open question. Some models suggest a thick atmosphere could persist if it were replenished by volcanic activity. Others suggest that Proxima's flare history would have stripped the atmosphere away billions of years ago, leaving a bare, irradiated rock. This is the cruel irony of the nearest star. It is a planet in the habitable zone. That planet orbits at a distance where liquid water could theoretically exist, and it may be one of the most inhospitable places within 4 light years. A world caught between fire and ice, bombarded by radiation from a star that cannot stop erupting. The nearest potentially habitable planet might be a graveyard, and yet it remains the closest we have. Everything else is farther. Every other star with every other planet sits deeper into the void, separated by even wider gaps of interstellar nothing. If the nearest destination is this hostile and this unreachable, the rest of the galaxy offers no easier answers. A civilization across the galaxy, 50,000 light years away, could have risen to technological maturity, broadcast signals for 1,000 years, exhausted its resources, and collapsed back into silence. And the light from their golden age would not have reached us yet. It would still be traveling, crossing the emptiness between spiral arms, passing through clouds of dust, weaving between stars that have no one around them to notice it passing. By the time that light arrives, the civilization that sent it might have been gone for longer than our species has existed. The galaxy does not connect things. It separates them. And it separates them on timescales that make mockery of every human idea about communication, contact, and shared experience. The silence we hear when we point our radio telescopes at the sky is not necessarily evidence that no one is out there. It may simply be evidence that the distances between stars are so extreme that even civilizations broadcasting at full power could exist for their entire history without a single signal reaching another living world in time to matter. This is the second layer of what distance does to the brain. The first layer, inside the solar system, destroyed the intuition that things you can see are things you can reach. This second layer destroys the intuition that things that exist at the same time can know about each other. Two civilizations, both alive, both curious, both pointing telescopes at the sky, separated by a gap so wide that each one lives and dies in the other's silence. Not because the signals are not sent, not because the technology is insufficient, but because the universe made the distances large enough that temporal isolation is the default condition of existence. Stars do not live in community with one another. They live in solitary confinement, separated by light years of void, each one wrapped in its own bubble of gravitational influence, each one surrounded by so much nothing that even the concept of neighboring star is a kind of generous fiction. Proxima Centauri is our neighbor, the way a lighthouse on the far side of the ocean is your neighbor. You can see its light. You can know it exists. You cannot reach it. You cannot talk to it. And between you and it, there is nothing but water and darkness for as far as the eye can see and far, far beyond. But here is where the story takes its next turn. Because everything we have just described, all of it, the silence between stars, the impossible gaps, the galaxy is a scattering of isolated points across 87,000 light years of vacuum. All of this is still just one galaxy. One single galaxy among trillions. And the distance between galaxies is not a larger version of the distance between stars. It is something else. Something that changes category again. Something that moves the problem from too far for any species to cross to too far for the structures of the universe themselves to remain connected. What comes next leaves the Milky Way entirely. And when you see what sits between one galaxy and the next, the emptiness within our own galaxy will begin to feel almost cozy by comparison. Everything we have covered so far took place inside a single galaxy. Every distance that broke your intuition about travel, every gap that outlasted civilizations, every silence between stars that made contact seem impossible, all of it happened within the Milky Way. One galaxy, one disk of stars, roughly 87,000 light years across, containing somewhere between 100 billion and 400 billion stars. Now we leave. And the moment we step outside the Milky Way, the rules change again. Not gradually. Not as a smooth escalation where the numbers simply get bigger. The rules change in kind. Because the distance between galaxies is not a scaled up version of the distance between stars. It is a new category. A category where the thing being separated is no longer individual stars or individual solar systems, but entire collections of hundreds of billions of stars. Entire galaxies, each one a sprawling island of matter, become the individual points. And the gaps between those points are so enormous that the distances inside any single galaxy begin to feel almost intimate. The nearest large galaxy to the Milky Way is Andromeda. It sits approximately 2.5 million light years away. That number deserves to be held in the mind for a moment, because it represents a shift so dramatic that comparing it to anything we have discussed so far almost feels dishonest. 2.5 million light years. If a beam of light left the Milky Way and traveled toward Andromeda, it would arrive in 2.5 million years. At the speed of Voyager One, the crossing would take roughly 44 billion years. That is more than 3 times the current age of the universe. The universe itself has not existed long enough for Voyager 1 to reach Andromeda. The fastest human-made object, given a head start at the dawn of time, would still not be there yet. Andromeda is not some dim smudge lost in the deep sky. Under dark skies, you can see it with the naked eye. It appears as a faint oval glow in the constellation bearing its name. A patch of light so soft, it barely registers against the background. What you are seeing when you look at it is the combined glow of roughly 1 trillion stars. Twice as many as our own galaxy contains. All of that light, from 1 trillion nuclear furnaces burning simultaneously, reduced to a smear of haze by sheer distance. And here is something that seems like it should be reassuring, but turns out to be the opposite. Andromeda and the Milky Way are moving toward each other. They are on a collision course. In roughly 4 to 5 billion years, the two galaxies will merge in an event that will reshape both of them into a single, larger, elliptical galaxy that astronomers have informally named Milkdromeda. This sounds violent. It is not. Or rather, the violence is not the kind you expect. When two galaxies collide, almost nothing actually hits anything else. The stars within each galaxy are so widely spaced, so separated by light years of empty vacuum, that when the two great disks pass through each other, individual stars slip between the gaps like two swarms of gnats passing through each other in the air. The gravitational interactions are enormous. Stars will be flung from their orbits. Some will be ejected from the merged galaxy entirely, sent hurtling into intergalactic space as orphans. Gas clouds will collide and compress, triggering fierce bursts of new star formation. The shapes of both galaxies will be distorted, stretched, warped into tidal tails and bridges of displaced stars. The merger will unfold over approximately 1 to 2 billion years. It will not be a single event, but a series of close passes, each one more disruptive than the last. On the first pass, the two galaxies will sweep through each other, their spiral arms unraveling into long tidal streamers of stars, flung outward by gravitational forces. The galaxies will separate briefly, their mutual gravity pulling them back together for a second, closer pass. Then a third. Each interaction will strip away more structure, more coherence, more of the elegant spiral geometry that defines both galaxies today. Eventually, the two cores will merge. The supermassive black holes at the center of each galaxy will spiral toward each other over millions of years, radiating gravitational waves as they close the gap. When they finally coalesce, they will form a single, larger black hole at the center of the new elliptical galaxy. The surrounding stars will settle into new orbits around this merged core, and the combined galaxy will gradually relax into a smooth, featureless ellipsoid. The spiral arms will be gone, the disk structure will be gone. The ordered rotation that defines a spiral galaxy will be replaced by a swarm of stars moving on randomly oriented orbits. Our own sun, if it still exists at that point, will likely survive the merger. The chances of any individual star being directly disrupted are extremely small, but the sun's orbit will be transformed. It could be flung closer to the merged galactic core, or pushed outward into the halo, or ejected into one of the tidal tails and left adrift in intergalactic space. The sky from Earth, or whatever planet might exist in 4 billion years, would be unrecognizable. The Milky Way's familiar band of light would be gone, replaced by the diffuse glow of an elliptical galaxy with no structure, no arms, no dust lanes, just a smooth haze of old stars slowly burning down. But the stars themselves will almost never touch. 2 objects each containing hundreds of billions of stars will pass through each other, and the odds of any 2 stars directly colliding are vanishingly small. That is how empty a galaxy is. Even when 2 galaxies occupy the same physical space at the same time, the matter within them barely notices. The emptiness is so total that collision, in the ordinary sense of the word, essentially does not apply. This tells you something important about the nature of cosmic structure. When the largest objects you can see are mostly emptiness, the emptiness is not a background detail, it is the dominant feature. Galaxies are not dense clusters of matter. They are sparse arrangements of matter floating in oceans of nothing, and the spaces between galaxies are oceans of nothing even more vast and more absolute than the spaces within them. This is where the shift happens. The question is no longer how far apart things are. The question becomes, what is the universe actually made of? And the answer at this scale begins to lean heavily toward one word: emptiness. But Andromeda is just the nearest large galaxy. It is part of a small family, and that family is itself an almost negligible mote inside a larger structure that stretches into dimensions of space the brain was never designed to process. The Milky Way and Andromeda belong to a collection of galaxies called the Local Group. This is a gravitationally bound cluster of more than 80 known galaxies spread across a volume approximately 10 million light-years in diameter. Most of the members are small. Dwarf galaxies, irregular galaxies, faint satellite systems orbiting the 2 dominant spirals like attendants around a pair of monarchs. The large and small Magellanic Clouds, visible from the southern hemisphere as bright patches in the night sky, are among them. The Triangulum Galaxy, roughly 3 million light-years from the Milky Way, is the 3rd largest member, 10 million light-years across. That is the span of our immediate galactic neighborhood. And within that span, 54 galaxies, 54 islands of stars, scattered across a volume so large that the distance from one side to the other would take light 10 million years to cross. The average separation between member galaxies is measured in hundreds of thousands of light years. Some sit relatively close together, others drift at the edges, barely held by the group's collective gravity. Now step further out. The local group is a small outlying structure on the edge of something much larger. The Virgo Cluster sits at approximately 54 million light-years from Earth. It is a true galaxy cluster, a gravitationally bound collection of over 1,300 galaxies, possibly as many as 2,000, held together by the collective pull of their combined mass. At its center lies M87, a giant elliptical galaxy famous for hosting one of the first black holes ever directly imaged. The Virgo Cluster is so massive that its gravity tugs on the local group, pulling us toward it even now. 54 million light-years. That number represents a distance where light from the Virgo Cluster left its galaxies roughly 54 million years ago, during the early Eocene, an era when the first primates were diversifying across tropical forests. Crocodilians basked in Arctic swamps, and the dinosaurs had already been extinct for 12 million years. The photons that arrived tonight have been traveling since a time when the Earth was almost unrecognizably warm, and the continents were still drifting toward their modern positions. You are seeing the Virgo Cluster not as it is now, but as it was in a geological epoch that no living human could identify from memory. The Virgo Cluster is also a violent place. It is not a serene gathering of galaxies drifting peacefully in formation. It is a gravitational arena where galaxies are being torn apart in real time. The space between the galaxies in a cluster is not truly empty. It is filled with an extremely hot, extremely thin gas called the intracluster medium, plasma heated to tens of millions of degrees by the gravitational energy released as galaxies fall inward toward the cluster center. This gas is so hot, it emits X-rays. Space-based X-ray telescopes have imaged the Virgo Cluster's intracluster medium and revealed a turbulent, dynamic environment where shock waves propagate across millions of light years, and rivers of superheated gas flow between galaxies. When a galaxy moves through this medium, it experiences ram pressure, a force analogous to the wind you feel when you hold your hand out of a car window at speed. But this wind is made of plasma at millions of degrees, and the galaxy is moving at hundreds of kilometers per second. The ram pressure strips gas from the galaxy like a hand peeling the skin from a fruit. Long tails of gas trail behind galaxies as they plunge through the cluster, their raw material for future star formation ripped away and scattered into intergalactic space. Astronomers have photographed these tails. They stretch for hundreds of thousands of light years behind some cluster galaxies, glowing faintly in hydrogen emission as the stolen gas cools and disperses. The galaxies being stripped will eventually run out of fuel for new stars. They will age and redden and fade, their spiral arms dimming as no new bright stars replace the ones that burn out, transformed into passive, featureless remnants, not by any internal process, but by the environment they fell into. The cluster itself is the killer, reaching inside each galaxy with invisible fingers of hot gas and pulling out everything it needs to survive. This is what a galaxy cluster looks like from the inside. Not a peaceful congregation, but a slow catastrophe. Galaxies falling inward, being stripped, being transformed, being consumed by the environment they inhabit. And the Virgo Cluster is just one of thousands of clusters in the observable universe, each one a gravitational furnace reshaping its members across hundreds of millions of years. That delay is not a quirk. It is a permanent feature of the distance. There is no way to see the Virgo Cluster as it currently exists. The information has not had time to arrive. It will not arrive for another 54 million years. This introduces something new. At intergalactic scales, distance and time become entangled in a way that does not apply inside a single galaxy. When you look at a star 20 light years away, the delay is trivial, 20 years. A noticeable gap, but one that falls within a human lifetime. When you look at the Virgo Cluster, the delay is longer than entire geological epochs. The universe you see at this distance is not the universe that exists. It is a fossil image, a snapshot of how things were in an era incomprehensibly remote from the present. And we are only 54 million light years out. The structures that come next will stretch this entanglement to its breaking point. In 2014, a team led by astronomer Brent Tully published a paper that redefined our understanding of where the Milky Way sits within the larger cosmic structure. Using the motions of galaxies as traces of gravitational flow, they mapped the currents of matter on enormous scales and identified a basin of gravitational attraction encompassing roughly 100,000 galaxies. They called it Laniakea, a Hawaiian word meaning immense heaven. Laniakea spans approximately 500 million light years. It is not a tight, dense structure like a galaxy cluster. It is more like a watershed, a vast region of space within which galaxies flow toward a common gravitational center. That center, the point toward which everything within Laniakea drifts, lies in the vicinity of the Norma and Centaurus clusters. It has been known for decades as the Great Attractor. The Great Attractor is not a single object. It is a region of enhanced mass density, a gravitational focal point containing many galaxy clusters that together pull on everything within Laniakea's reach. Its total mass is estimated at roughly 10 million billion times the mass of our Sun. It sits approximately 150 to 250 million light years from Earth, partially hidden behind the dense disk of the Milky Way in a region astronomers call the zone of avoidance, where the dust and stars of our own galaxy block the view. 500 million light years across, 100,000 galaxies, all flowing toward a gravitational center that we cannot even fully see because our own galaxy is in the way. This is the structure within which the Milky Way, the Andromeda galaxy, the local group, and the Virgo cluster are all embedded. We are not at the center. We sit on the outskirts, drifting inward along the flow like a leaf caught in a slow, enormous current. And here is the detail that stops the breath. Laniakea is not gravitationally bound. Despite its immense size and its 100,000 galaxies, the structure is not dense enough to hold itself together against the expansion of the universe. It is a temporary pattern, a transient arrangement of matter that will eventually be pulled apart by dark energy. Billions of years from now, the individual components of Laniakea, the galaxy clusters and groups that currently flow toward the Great Attractor, will be separated by the accelerating expansion of space itself. The supercluster will dissolve, the currents will fade, the galaxies will drift apart into isolation. The structure we call home at the larger scale is not a permanent home. It is a brief congregation, a gathering that will disperse. But the most disorienting feature of the universe at this scale is not the size of the structures. It is the size of what sits between them. In 1981, astronomer Robert Kirshner and his colleagues were mapping the distribution of galaxies across a section of sky near the constellation Boötes when they found something that should not exist. A region of space roughly 330 million light years across that was almost completely empty. Not thinly populated, not sparse, empty. Where the expected number of galaxies for a volume of that size was approximately 2,000, they found fewer than 10. Subsequent surveys extended the count to roughly 60, but the deficit remained staggering. a sphere of space larger than most superclusters, containing barely 3% of the galaxies it should. They called it the Boötes Void. Some astronomers call it the Great Nothing. The Boötes Void is not a hole in the universe. It is a natural feature of the large-scale structure of the cosmos. The universe, when mapped at scales of hundreds of millions of light years, does not look like a uniform sea of galaxies evenly spread in every direction. It looks like a web. Thin filaments of galaxies and galaxy clusters weave through space like threads in an enormous three-dimensional net. At the intersections of the filaments, great clusters accumulate. And between the filaments, filling the vast majority of the volume, are voids. The voids are not merely empty, they are structurally dominant. When astronomers map the distribution of matter across the observable universe, what they see is that the filaments and clusters, everything that contains stars and planets and light and life, occupy a small fraction of the total volume. The voids occupy most of it. The universe is not a collection of objects with gaps between them. It is a collection of gaps with occasional thin threads of objects draped across the surfaces. The Boötes Void is the largest of these gaps that has been clearly identified and measured in the nearby universe. A sentient being born on one of its few scattered galaxies would look out at the night sky and see almost nothing. No bright band of a galactic neighbor. No nearby clusters glowing in the distance. Just an enormous, terrifying emptiness stretching hundreds of millions of light years in every direction. They might conclude, reasonably, that the universe contained nothing but their own lonely island and an infinite expanse of dark. And the Boötes Void, as vast as it is only a moderately large example of what the universe does with emptiness. The large-scale structure of the cosmos is organized at scales that dwarf even the superclusters. Filaments of galaxies stretch for billions of light years. Sheets of matter, called walls, extend across enormous surfaces. And the voids they enclose grow proportionally. In 2013, a team of American and Hungarian astronomers, led by István Horváth, was analyzing data from the Swift gamma-ray burst mission when they identified a clustering of gamma-ray bursts at a specific distance from Earth that suggested the presence of an enormous structure. Subsequent analysis estimated its size at approximately 10 billion light-years. They called it the Hercules Corona Borealis Great Wall, 10 billion light-years. That is roughly 1/9 the diameter of the entire observable universe. A single structure, a filament or sheet of galaxy clusters, stretching across a span so large that light from one end would need 10 billion years to reach the other. In 2025, a reanalysis suggested the structure might be even larger, possibly up to 15 billion light-years, and closer to Earth than previously estimated. Its existence remains debated. Some astronomers argue it could be an artifact of uneven data coverage or statistical noise in the gamma-ray burst distribution. Others maintain that the clustering is real and represents a genuine feature of the cosmic web. If it is real, the Hercules Corona Borealis Great Wall is the largest known structure in the observable universe, and its sheer size creates a problem for cosmology. The cosmological principle, one of the foundational assumptions of modern physics, holds that the universe is homogeneous and isotropic at sufficiently large scales. That means if you zoom out far enough, the distribution of matter should look roughly the same everywhere, in every direction. Structures like the Hercules Corona Borealis Great Wall push against this principle. A feature 10 billion light-years across challenges the idea that there is a scale at which everything averages out. The universe may be lumpier, more structured, more organized by filaments and voids than the models assumed. And within this web, within these filaments and walls and voids, the pattern repeats at every level. Galaxies cluster into groups, groups cluster into clusters, clusters align along filaments. Filaments frame voids, voids fill most of the volume. And the objects, the galaxies and stars and planets and people, occupy a fraction so small that if you selected a random point anywhere in the observable universe, the overwhelming probability is that you would find yourself in a void, far from any filament, far from any cluster, far from any galaxy, surrounded by nothing, in every direction, for hundreds of millions of light years. This is the third distance that breaks your brain, not because it is the largest number yet, though it is, but because it changes what distance means at a structural level. Inside the solar system, distance was a problem of travel. Between stars, distance was a problem of survival and time. Between galaxies, distance was a problem of isolation and communication lag. But at the scale of the cosmic web, distance stops being a problem at all, because the word problem implies something that could, in principle, be solved. At this scale, the emptiness is not an obstacle between destinations. It is the primary feature of the universe. The destinations, the filaments and clusters and galaxies are the secondary feature. They are the exceptions. The thin, bright threads stitched across an ocean of dark. The universe is not a place filled with things and separated by gaps. It is a place filled with gaps and decorated very occasionally by things. The architecture of reality at this scale is not matter. It is emptiness. And the farther you zoom out, the more clearly that architecture dominates. Consider the Boötes Void one more time. 330 million light years across. 60 galaxies inside it, where 2,000 should be. If you could somehow stand at the center of the void and look outward, every galaxy you could see would be inconceivably far away. The nearest wall of the cosmic web would sit more than 100 million light years from you. Light from the closest significant cluster would have been traveling since before complex life existed on Earth. You would be the most isolated conscious being in the observable universe, surrounded by a silence and an emptiness so total that the space between stars within a single galaxy would feel like a crowded room by comparison. The discovery of the Boötes Void was itself a lesson in how emptiness reveals itself. In the late 1970s and early 1980s, Robert Kirshner and his colleagues were conducting a redshift survey, measuring the distances to galaxies in a specific region of sky by analyzing how much their light had been stretched by the expansion of the universe. Redshift surveys were the primary tool for mapping the three-dimensional distribution of galaxies. You point a telescope at a galaxy, you measure its redshift, you calculate its distance, do this for enough galaxies, and you build a map. What Kirshner's team expected to find was a roughly uniform scattering of galaxies at various distances, consistent with the prevailing assumption that matter was distributed more or less evenly at large scales. What they found instead was a gap, a region where the redshift simply stopped. Galaxy after galaxy appeared at distances closer than the void and farther than the void, but within it, almost nothing. The team published their result in 1981 under a title that captured the shock of the finding: 1 million cubic megaparsec void in Boötes. The discovery prompted a wave of follow-up observations. objective prism surveys search for emission line galaxies that might have been missed. The infrared astronomical satellite scanned the region for dust-obscured galaxies invisible in optical light. Over the decades, the count inside the void climbed from 8 galaxies to roughly 60. But the void itself held firm. It was real, it was enormous, and it was not a flaw in the data, it was a feature of the universe. Later, much larger surveys confirmed that the Boötes Void was not an anomaly. It was a particularly dramatic example of a phenomenon that pervades the cosmos. The Sloan Digital Sky Survey, which mapped the positions and redshifts of millions of galaxies across a large fraction of the sky, revealed the cosmic web in stunning detail. The maps looked like cross-sections of a sponge. Thin walls and filaments of galaxies surrounded enormous empty bubbles, void after void after void, stretching across hundreds of millions of light years. The universe at large scales was not a uniform sea. It was a foam. The galaxies lived on the surfaces of the bubbles. The interiors were almost completely empty. The 2-degree field galaxy redshift survey and the later dark energy spectroscopic instrument survey extended this mapping further, confirming the web-like structure at greater and greater distances. The pattern was consistent everywhere. Filaments, walls, clusters at the intersections, and voids filling the rest. The voids are not exceptions. They are the rule. They are what most of the universe looks like. The filaments and clusters, with all their galaxies and stars and planets, are the exceptions. Thin membranes of matter stretched across an emptiness that fills most of the volume of reality. To understand this structure, imagine a kitchen sponge the size of a continent. The solid material of the sponge, the thin walls and strands that give it shape, represents all the galaxies and clusters in the universe. The holes, the air pockets, the empty interiors of every bubble represent the voids. Now, notice that the holes take up far more volume than the walls. The sponge is mostly air. The universe is mostly void. The matter is just the scaffolding, and the Boötes Void is just one void. There are thousands of voids in the observable universe, some smaller, some possibly larger. Together, they account for the vast majority of the universe's volume. The cosmic web, the structure that contains every galaxy and every star and every planet and every atom of every living thing that has ever existed, is a thin, fragile scaffolding stretched across an abyss. That scaffolding is not permanent. It is not protected. And the force that is slowly, inexorably tearing it apart is already at work. It has been at work for approximately 5 billion years, accelerating every moment, growing stronger with every passing epoch. Soon, you will understand what that force is, what it is doing to the structures we have just described, and why the final distances in the universe are not merely large but permanent. The emptiness we have mapped here, the voids, the gaps between filaments, the 330 million light-year deserts of nothing, these are the universe as it currently exists. What comes next is the universe as it is becoming, and what it is becoming is lonelier than anything we have described so far. We have crossed the solar system, we have crossed the gap between stars, we have crossed the galaxy, the space between galaxies, the superclusters, the filaments, and the voids. At every stage, the distance changed category. Travel became impossible, communication became impossible, even awareness of what exists at the other end became uncertain. Each new scale destroyed a different layer of the assumption that the universe is a connected place. Now we arrive at the last distances, The ones that do not merely defeat travel or contact or knowledge, the ones that are, by the laws of physics themselves, permanent, absolute, built into the structure of reality in a way that no technology, no breakthrough, no amount of time will ever undo. These are the distances at the edge of the observable universe. And they do not break your brain because they are the biggest numbers on the list. They break your brain because they reveal that the universe has a boundary, not a wall you can touch, but a horizon beyond which nothing you do will ever matter. And that boundary is closing in. Start with the farthest things we have ever seen. In 2024, the James Webb Space Telescope confirmed the most distant galaxy ever observed. The object, catalogued by the JADES survey team, emitted the light we are now receiving when the universe was only approximately 290 million years old. That light has been traveling for over 13.4 billion years. It crossed a universe that was expanding the entire time, which means the galaxy that emitted it is now far more distant than 13.4 billion light years. Due to the expansion of space during the journey, that galaxy currently sits at a co-moving distance of approximately 29 billion light years from Earth. That last sentence is worth pausing on, because it contains one of the most counterintuitive truths in all of cosmology. The light is 13.4 billion years old, but the object that emitted it is now 33 billion light years away. How can something be farther away than the distance light could have traveled in the age of the universe? The answer is that space itself has been expanding during the entire journey. The photon left the galaxy 13.4 billion years ago. As it traveled toward us, the space behind it stretched. The galaxy receded. The distance between its starting point and its destination grew even as the photon crossed it. By the time the photon arrived, the galaxy that emitted it had been carried by the expansion of space to a location far beyond the distance that light alone could account for. This is not motion in the ordinary sense. The galaxy didn't fly through space to reach its current position. Space itself expanded, carrying the galaxy with it. And this is happening everywhere, at every scale, in every direction. The fabric of the universe is stretching. Every point is moving away from every other point. And the farther apart two points are, the faster the expansion carries them apart. This is where the most important boundary in the universe reveals itself. Think of it this way. At modest distances, the expansion of space is slow. Light can easily outrun it. A photon emitted by a galaxy a few billion light years away will arrive without difficulty, because the expansion between here and there is not fast enough to prevent the crossing. But at greater distances, the expansion rate increases. At some critical distance, the expansion of space between 2 points becomes so rapid that it matches the speed of light. A photon emitted from a galaxy at that distance would travel toward us at the speed of light. But the space it needs to cross would be stretching at the same rate. The photon would run in place forever, never gaining ground, never arriving. And beyond that distance, the expansion wins. Space stretches faster than light can cross it. A photon emitted from a galaxy beyond that threshold is not just delayed. It will never arrive, not in a billion years, not in a trillion, not ever. The signal is lost, permanently, to the expansion of the universe. This boundary is called the cosmic event horizon. It is not a physical wall. It is not a surface you could touch or see. It is a mathematical limit, a distance beyond which no signal, no light, no information of any kind will ever reach you, no matter how long you wait. Current estimates place it at a comb-moving distance of approximately 16 to 17 billion light-years from Earth, though the precise value depends on the future behavior of dark energy. Every galaxy beyond the cosmic event horizon is permanently inaccessible. Not practically inaccessible, the way Proxima Centauri is inaccessible because we lack the technology. Not inaccessible on human timescales, the way the other side of the Milky Way is inaccessible because the journey would take longer than civilizations last. Permanently inaccessible. The laws of physics themselves forbid any interaction, any communication, any knowledge of what is happening there. Those galaxies are gone. They are part of a universe we can never participate in. And the event horizon is not static. It is shrinking. Because the expansion of the universe is accelerating. This is the discovery that earned Saul Perlmutter, Brian Schmidt, and Adam Rees the Nobel Prize in Physics in 2011. By studying distant supernovae, they demonstrate that the expansion of space is not slowing down under the pull of gravity, as most physicists expected. It is speeding up. Something, a force or a property of space itself that physicists call dark energy, is pushing the expansion faster and faster with every passing era. For over 2 decades, the standard assumption was that dark energy behaves like a cosmological constant, a fixed property of empty space that exerts the same repulsive pressure everywhere and at all times. If that were true, the future of the universe would be straightforward. The expansion would continue to accelerate at a predictable rate, and the long-term fate of the cosmos could be calculated with reasonable confidence. Recent results have introduced uncertainty into that picture. In 2024 and 2025, the Dark Energy Spectroscopic Instrument, known as DESI, released findings from its first year of observations mapping the 3-dimensional distribution of millions of galaxies across billions of light years. The data suggested that dark energy may not be constant. There were hints, still preliminary and not yet confirmed at the level of statistical certainty required for a definitive claim, that the strength of dark energy may be changing over time. If dark energy is weakening, the acceleration of expansion could slow in the far future. If it is strengthening, the acceleration could intensify beyond current projections, potentially leading to a scenario in which the expansion eventually tears apart galaxies, stars, and even atoms in an event physicists call the Big Rip. The honest scientific position is that we do not yet know which of these futures is correct. The DESI results are suggestive but not conclusive. Additional years of data collection and analysis are needed before the behavior of dark energy can be pinned down. What is certain is that dark energy is real, that the expansion is currently accelerating, and that the consequences for cosmic distance are already unfolding. Whether those consequences intensify, stabilize, or eventually reverse is one of the most important unanswered questions in all of physics. Dark energy constitutes approximately 68% of the total energy content of the universe. It is the dominant force shaping the large-scale future of everything. And its effect on cosmic distances is devastating. Because the expansion is accelerating, galaxies that are currently within the observable universe, galaxies whose light we can still see, are being pushed beyond the event horizon. They are receding faster and faster. And one by one, they are crossing the line beyond which their light will never reach us again. Estimates suggest that approximately 160 billion stars cross the cosmic event horizon every year, carried away by the expansion of space into permanent inaccessibility. They do not vanish instantly. Their light redshifts stretches to longer and longer wavelengths, growing fainter and redder over billions of years until it becomes undetectable. They fade, they dim, and then they are gone. The observable universe, the portion of reality we can see and in principle interact with, is losing members, constantly, irreversibly. The cosmic census is shrinking even as the universe itself grows. And here is the number that puts it in its starkest terms. Current calculations suggest that approximately 94% of the galaxies within the observable universe are already beyond the cosmic event horizon. They are still visible because the light they emitted billions of years ago is still arriving, but they are already unreachable. A signal sent toward them today at the speed of light would never arrive. They are ghosts. Images of galaxies that exist in a part of the universe we have already lost 94%. That means only about 6% of the galaxies we can currently see are still within the portion of the universe we could theoretically interact with. And that 6% is shrinking. In the far future, trillions of years from now, the consequences of this will be total. The accelerating expansion will push every galaxy that is not gravitationally bound to us beyond the event horizon. The Virgo Cluster, the Laniakea supercluster, the cosmic filaments and walls and voids, all of it will recede into silence. The only galaxies that will remain accessible are those bound to us by gravity strong enough to resist the expansion. That means the local group, roughly 80 galaxies, dominated by the Milky Way and Andromeda, clinging together in a gravitational embrace, while the rest of the universe disappears around them. Eventually the Milky Way and Andromeda will merge. Triangulum will fall in. The dwarf satellites will be absorbed. What remains will be a single large elliptical galaxy, burning through its remaining fuel, surrounded by darkness in every direction. The cosmic microwave background, the oldest light in the universe, will have redshifted beyond all detection. The other galaxies, the filaments, the clusters, the great walls, will have faded below any observable threshold. A civilization born in that era would look out at the sky and see nothing. No other galaxies, no evidence of a larger universe, no sign that anything exists beyond their single island of stars. They would have no way to discover the Big Bang. The evidence for it, the cosmic microwave background radiation first detected by Arno Penzias and Robert Wilson in 1965, would have long since stretched to wavelengths too long to detect. The expansion of space that carries the evidence of the universe's origin would have erased that evidence completely. A civilization born in the deep future would see a static, unchanging sky and reasonably conclude that their galaxy was all there was. That the universe was small, cold, and eternal. They would be wrong, but they would have no way to know it. Think about what specific knowledge would be lost. A civilization born in the deep future. Trillions of years from now, inside the merged remnant of the Milky Way and Andromeda, would have access to a single large elliptical galaxy and nothing else. They would see their own stars. They could map their own galaxy's structure. They could study stellar evolution, nuclear physics, chemistry, gravity. They would develop sophisticated science. They might even consider themselves advanced. But they would be missing the largest truths about reality. They would have no evidence that the universe is expanding because every galaxy outside their local group would have long since redshifted beyond detection. The expansion would be invisible. Without the ability to observe distant galaxies receding, they could not derive the Hubble constant. Without the Hubble constant, they could not infer the Big Bang. They would look at their galaxy and see a stable, perhaps eternal structure. The idea that the universe once existed as a hot, dense plasma compressed into a volume smaller than an atom would seem like fantasy. There would be no evidence for it. They would have no cosmic microwave background to detect. The photons that currently fill every cubic centimeter of space would have been stretched by the expansion to wavelengths so enormous, so far beyond the microwave or radio spectrum, that no instrument could plausibly pick them up. The afterglow of creation would be gone. The single most important observation in the history of cosmology would be permanently unavailable. They would have no evidence of dark energy. Without distant galaxies to serve as markers, the accelerating expansion that is reshaping the universe right now would be undetectable. They could not measure what they could not see receding. Dark energy, the dominant component of the universe's energy budget, the force responsible for the isolation their civilization was born into, would be completely invisible to them. They would look at the sky and construct a cosmology based on what they could observe. That cosmology would be self-consistent, internally logical, supported by every observation available to them, and it would be catastrophically wrong. It would describe a small, static, eternal universe containing a single galaxy. Every major discovery of 20th and 21st century cosmology, the expansion, the Big Bang, the cosmic microwave background, dark energy, the cosmic web, the existence of trillions of other galaxies would be not merely unknown but unknowable. The evidence would have been carried beyond the horizon by the very force those future scientists could never detect. This is not a thought experiment about the limits of technology. It is a consequence of distance. The expansion of space does not merely separate objects. It separates eras of understanding. It creates a universe where the truth about reality has an expiration date. The information is available now. It will not be available forever. Distance at this final scale is an eraser. This is perhaps the most haunting consequence of cosmic distance. Not that the universe is large, not that most of it is unreachable, but that the evidence of its existence is being erased. The universe is not just separating things, it is destroying the information that those things ever existed. The expansion of space is not merely a barrier, it is an active process of cosmic forgetting, wiping the sky clean, pulling the evidence of reality's true scale beyond the reach of any future observer. We happen to live in an era when the evidence is still visible. The cosmic microwave background still bathes us in its ancient glow, carrying information about the first 400,000 years of the universe. Distant galaxies still send their light across billions of light years, testifying to a cosmos far vaster than what will one day be visible. We can see the filaments, we can map the voids, we can measure the expansion and calculate what is being lost. But this window is temporary. The universe is in the process of closing the curtains, and once they close, they never reopen. This brings us to the final question, the one that sits underneath every distance we have measured, every boundary we have crossed, every void and filament and horizon we have traced. What does all of this mean? Not what does it mean scientifically. We have covered the science. We know the numbers. We know the names. The question is what it means to be a conscious being in a universe organized this way. Because the universe is not merely large, largeness alone would be manageable. A large universe could still, in principle, be traversed, mapped, known. What makes this universe terrifying is not its size, but its structure. It is organized in layers of separation, each one more absolute than the last. At the solar system scale, distance separates you from places you can see but cannot reach in a lifetime. At the interstellar scale, distance separates you from places you could not reach, even if your civilization lasted 1,000,000 years. At the galactic scale, distance separates you from regions that exist within your own galaxy, but are so remote that light from them has been traveling since before your species evolved. At the intergalactic scale, distance separates you from structures so vast that even the concept of travel loses all meaning. And at the cosmological scale, distance becomes permanent. It is not a gap to be crossed. It is a severance, a line drawn by the expansion of space itself, beyond which no signal, no ship, no thought will ever pass. Each layer of this hierarchy does not simply add to the one before it. It changes the nature of what separation means. The transition from too far to drive, to too far to survive, to too far to communicate, to too far to ever know existed, is not a smooth gradient. It is a series of cliffs, and at each cliff, a different human assumption about connection, reach, and significance falls away. We assume that the universe is a place, that it is an environment, that it has a geography, and that geography connects its parts the way roads connect cities. That assumption fails at every scale we have examined. The universe is not a connected environment. It is a hierarchy of isolations. Each level of the hierarchy is more severe than the last, and at the final level, the isolation becomes absolute. The cosmic microwave background, the oldest light in the universe, is often described as the edge of the observable universe. It is not, strictly speaking, a wall. It is a surface of last scattering, the moment approximately 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely for the first time. Every photon in the cosmic microwave background has been traveling since that moment. When those photons reach your telescope, you are looking at the most distant thing it is possible to see. Not the most distant thing that exists, the most distant thing from which light has had time to arrive. The cosmic microwave background was discovered almost by accident. In 1965, Arno Penzias and Robert Wilson, two radio astronomers working at Bell Telephone Laboratories in New Jersey, were trying to calibrate a large horn antenna originally built for satellite communication. They kept picking up a persistent low-level noise in their instrument, a faint hiss that appeared in every direction they pointed the antenna at every time of day, in every season. They cleaned the antenna. They removed pigeon droppings that had accumulated inside the horn. They checked every component. The noise remained. What they were hearing was the afterglow of the Big Bang itself. The entire observable universe is bathed in microwave radiation left over from the moment, roughly 380,000 years after the universe began, when the primordial plasma cooled enough for the first atoms to form. Before that moment, the universe was opaque. Photons could not travel freely because they were constantly scattered by free electrons in the hot plasma. When the electrons combined with protons to form neutral hydrogen, the photons were released. They have been traveling ever since, cooling and stretching with the expansion of space, from a blinding white-hot glow to the faint microwave whisper that Penzias and Wilson detected. That whisper is everywhere. It fills every cubic centimeter of space. It arrives from every direction with almost perfect uniformity, varying by only 1 part in 100,000 across the sky. Those tiny variations, mapped in extraordinary detail by satellites like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck mission, encode the density fluctuations of the infant universe. These slightly denser regions became the galaxy clusters and filaments we see today. The slightly less dense regions became the voids. The entire large-scale structure of the cosmos, every filament, every wall, every void, every supercluster, was seeded by those microscopic variations in the temperature of light released 13.8 billion years ago. The cosmic microwave background is not just an observation, it is a boundary. It marks the farthest surface from which any electromagnetic signal can ever reach us. Beyond it lies the era before atoms existed, a time when the universe was opaque and no light could escape. We can never see past it. It is the wall at the edge of visibility. Beyond that surface, the universe continues. It does not stop at the edge of what we can observe. Most cosmological models suggest the full universe is vastly larger than the observable portion, possibly hundreds of times larger, possibly infinite. But none of that additional volume will ever be accessible to us. It exists beyond the cosmic event horizon. It's real, presumably filled with galaxies and stars and voids and filaments of its own, but it is permanently, irrevocably cut off. The observable universe, 93 billion light-years in diameter, is not the universe. It is a window, and the window is shrinking. This is the final distance that breaks the brain. Not a number, not a measurement, a realization. The universe is not a thing you live inside. It is a process that is pulling itself apart. The distances between structures are growing. The event horizon is swallowing galaxies. The evidence of the cosmos's true scale is being erased. And the end state, the deep future toward which all of this is heading, is a sky with nothing in it. A single galaxy burning down its last reserves of hydrogen, surrounded by an emptiness so total and so permanent that no observer within it could ever reconstruct the truth of what the universe once was. Every star you see tonight is a temporary offering. Every galaxy visible through a telescope is a message that will eventually stop arriving. Every filament, every cluster, every wall and void and supercluster in the cosmic web is a feature of a universe that is in the process of dissolving its own structure. The most terrifying distances in space do not break your brain because they are large. They break your brain because they are layered. Because each layer reveals a new kind of separation. Because the universe is not merely big, but organized around inaccessibility at every level. Because the farther out you look, the less the universe resembles a place, and the more it resembles a farewell. We are standing in a window of cosmic time when the universe still reveals itself, when the light from distant galaxies still arrives, when the microwave background still glows, when the web of filaments and voids is still visible, still mappable, still knowable. This era will not last. The universe will not always show its full hand. One day, the sky will darken. The evidence will fade, and whatever conscious beings remain will look up and see only their own stars reflected against a wall of black. They will not know what they lost. They will not know that the universe was once a web of light, stretching across 93 billion light-years. They will not know about the filaments, the voids, the great walls, the superclusters. They will not know about the cosmic microwave background, or the Big Bang, or the era when trillions of galaxies blazed in every direction. They will see darkness and call it the universe, and they will be wrong. But the evidence that they are wrong will have long since crossed the horizon and disappeared. That is the deepest thing that distance does. It does not just separate objects, it separates eras of knowledge. It creates a universe where the truth about reality is available only temporarily, only to observers lucky enough to exist during the brief window when the light still arrives. We are those observers. This is that window. And the distances we have crossed tonight, from the surface of the Earth to the edge of the observable universe, are not just measurements of how far apart things are. They are measurements of how much of reality is slipping away. The universe is not waiting to be explored. It is not a frontier that rewards patience and ambition. It is a structure built around separation, and the separation is winning. Every year, more galaxies cross the horizon. Every era, the sky grows emptier. Every epoch, the distance between what is knowable and what exists grows wider. And here, tonight, on this small planet orbiting one ordinary star in the outer arm of one ordinary galaxy, we still have the light. We still see the web. We still hear the faint hiss of the cosmic microwave background whispering its ancient story. We are the ones who know how large the universe truly is, not because we are special, but because we are early, because the window is still open, because the distances have not yet finished their work. One day, they will. And when they do, no one will ever know what we knew. The light is still arriving. For now.